Launching a modern strike fighter from a moving runway at sea subjects an airframe to extreme physical violence. The machine goes from a standstill to flight speed in under 3 seconds, fighting gravity and thousands of pounds of kinetic drag. Inside that environment is a single human operator. A pilot must manage the immense physical stress of the launch while simultaneously interpreting thousands of incoming data points from the aircraft's sensors. Operating the Super Hornet requires managing an immense cognitive load, a challenge solved by the structural logic of the NATOPS Flight Manual. The manual's opening letter of promulgation establishes its core philosophy. This document provides a positive approach toward improving combat readiness and achieving a substantial reduction in the aircraft mishap rate by strictly standardizing procedures across the entire fleet. Yet the architecture is deliberate in its flexibility. Commanding officers retain the authority to modify these procedures to test and assess new ideas in the field. The manual is designed as a living framework that adapts to the realities of combat aviation. That framework carries the absolute authority of the Navy, codified by the commander of the Naval Air Systems Command. Mastering the FA-18 requires mastering this text first. The manual functions as the literal operating system for the human pilot. To understand the operational logic of the aircraft, we start with the manual's primary navigational tool, the 11-section index. The structure begins with strict hardware definition. Part 1 defines the physical boundaries, dimensions, and complete internal systems of the jet long before the text introduces a single human procedure. Only once the hardware is mapped does the manual transition to human action. Sections 3 and 4 introduce the daily choreography of normal flight procedures and the specific handling characteristics of the aircraft in the air. The next sections deal entirely with edge cases. Here, the manual codifies exact responses for emergency procedures and the total loss of visual reference during all-weather operations. The remaining sections act as highly specialized reference tables. They provide exhaustive data on communication protocols, weapon systems deployment, and raw performance metrics required to execute a mission. The sequence is intentional. A pilot must sequentially build their mental model from the foundational metal and wires of the airframe upward into the complex algorithms of emergency response. Section 2 is an exhaustive inventory of the Super Hornet's physical and digital plumbing. It details intricate energy routing like the AMAD, which powers hydraulic pumps and generators, and the FCS, the electronic interface translating pilot stick movements into digital flight commands. The FCS requires its own massive subsection because the Super Hornet is aerodynamically unstable by design. The pilot does not directly fly the plane. Instead, flight computers interpret pilot inputs, executing thousands of micro-adjustments per second to prevent the airframe from departing controlled flight. The manual also mandates mastery of the systems keeping the operator combat effective. The environmental control system manages cabin pressurization, avionics proling, and pilot life support. The Joint Helmet-Mounted Cueing System is a specialized visor projecting flight data and targeting information directly into the pilot's field of view. The NATOPS manual treats the pilot as a systems manager first. Actual flying is simply the byproduct of managing these deeply interconnected networks. Once the hardware is understood, Part 3 strictly divides the application of that hardware based on the operating environment. Chapter 7 details shore-based procedures. This is the traditional aviation life cycle: pre-flight checks, engine start, taxiing, a standard runway takeoff, and standard visual flight rules landing patterns. Chapter 8 outlines carrier-based procedures. The introduction of a pitching, moving flight deck demands an entirely distinct and high-risk procedural set. Standard checklists are replaced. Taxiing is now a highly coordinated movement on a crowded deck. The standard runway takeoff is entirely discarded in favor of catapult hookup and catapult launch procedures.
A critical addition is catapult trim. Accelerating to flight speed in 2 seconds exerts massive rotational forces on the airframe. The pilot must input precise, weight-dependent calculations into the flight computers to ensure the jet holds the exact necessary pitch as it clears the deck. Recovery operations shift from standard runway wheel braking to the violent deceleration of an arrested landing. To achieve this safely, pilots utilize ACL mode approaches. Automatic carrier landing is a system that links the aircraft's flight computers directly to the ship's radar, guiding the jet down to the deck automatically. Chapter 9 holds highly specialized procedures that transcend location. This includes operating as an airborne tanker using the ARS. An air refueling store is an external pod that allows the fighter to carry and dispense fuel to other aircraft. It also covers executing missions with NVDs. Night vision devices are helmet-mounted optics that amplify ambient light for flying in near-total darkness. In naval aviation, the environment dictates the exact procedure. The manual physically segregates shore and sea operations because the margins for error on a carrier allow zero overlap with standard runway logic. After establishing normal operations, Part 4 systematically strips away nominal conditions to explore the absolute physical limits of the airframe. Pilots study handling qualities to understand how the jet physically responds when pushed through extreme acceleration or past its AOA limits. Angle of attack is the angle between the aircraft's wing and the oncoming flow of air. Section 11.3 details OCF. Out-of-control flight is the aerodynamic state where the aircraft stops responding predictably to pilot inputs and begins to tumble or spin. The manual provides precise protocols for departure resistance and spin recovery systems. Section 11.4 outlines degraded mode handling qualities. The text mathematically accounts for flying with broken control surfaces, like a trailing edge flap failure, or dealing with extreme lateral weight asymmetry from uneven weapon loads. When the flight computers detect these physical failures, they automatically reconfigure the control laws to keep the crippled jet flying. The pilot must memorize exactly how the handling characteristics will change under these new degraded conditions. Part 4 ensures the pilot understands the exact aerodynamic thresholds where the aircraft will simply stop flying normally. This leads directly into Part 5, Emergency Procedures, which categorizes worst-case scenarios chronologically into ground, takeoff, and in-flight emergencies. This diagram shows the structural logic of the manual. Every emergency listed in Chapter 15 maps directly back to a baseline system learned in Chapter 2. A failure in the avionics subsystem directly dictates the exact response required to survive a dual-mission computer failure. The manual identifies the immediate action items. These are the critical few steps a pilot must execute entirely from memory, instantly, before they have the time to physically open the checklist. The text outlines precise steps for catastrophic in-flight events, a fuselage fuel leak, a double transformer rectifier failure, or the sudden onset of hypoxia due to a loss of cabin pressure. Even in a rapidly deteriorating crisis, the NATOPS framework forces the pilot into a pre-calculated algorithmic troubleshooting loop. It replaces human panic with engineered logic. Inside this architecture, an emergency is simply a nominal system running an alternative set of instructions. Operating the Super Hornet requires an operator to scale an immense wall of data. From memorizing the plumbing of the fuel transfer system, to calculating catapult trim, to diagnosing a computerized flight control failure mid-spin. The combat effectiveness of the FA-18 relies entirely on the standardization of the human mind operating it. The NATOPS manual focuses on producing incredibly efficient managers of risk and machinery in an FA-18E or F variant. Every flight of the Super Hornet represents the step-by-step execution of the rigorous architecture within the NATOPS manual.